Welcome to this lecture series on electric machine design. This is lecture number 7 of the series, and in this lecture we are going to talk about design details of the transformer. Now, first and foremost, as designers, as engineers, there are some important specifications that have to be kept in mind while transformers are designed. Let's list them out one by one. You have the first specification is the rating, the capacity or the output. This is in kVA. The voltage or the voltage rating for HV and LV. Additionally, you may have tappings, so if there are any tappings you have to factor in those as well. The operating frequency F, which is in hertz. The number of phases, it could either be a single phase transformer or a 3-phase transformer. Type of connection, in 3-phase it could be a star star, star delta, and likewise. It could be rating, whether it's continuous or for a short time. Cooling, whether it's forced or natural. The type, whether it is core type or shell type. Then we have the efficiency per unit impedance. Temperature rise, etc. So these are some of the specifications that you must keep in mind, that any designer must keep in mind. So the design of transformer, it can be split up into 4 different steps. You have the first output equation, dimensions of the transformer, of the windings. Then you have the overall dimensions, that is the dimension of the transformer, the winding, the core, etc. Then you have the cooling apparatus. You have to design the cooling apparatus for the transformer. And then you have estimation of some values such as no load current, iron losses, eddy current losses, resistance, reactance, etc. So this is, broadly speaking, the design of a transformer is in these 4 categories. Okay. We know in general, if we have a single phase transformer, and it looks something like this. If it is a single phase core type transformer, you have the source which excites this, and based on this you have a set number of turns in the secondary. So if I label this as EP, this I label ES, this is the voltage of the primary side, this is the voltage of the secondary side. EP and ES refers to the induced voltage in the primary and induced voltage in the secondary. And if this is the flux in the core like this, we know that the flux phi in the transformer is a sinusoidal function. So we can write the flux phi as phi max sine of omega t, where this phi max is the maximum value of flux, right? Omega is the angular frequency, and it is 2 pi f radians per second. So based on this flux, an EMF is induced in the primary, which is denoted by EP, and it is equal to the number of turns in the primary and this times the derivative of the flux. So this can be written as omega n1 phi max cos omega t. This is the EMF induced in the primary. So you can see that the EMF leads the flux by an angle of 90, right? Cos omega leads sin omega by 90. And if you see this EP, if I should give it the name E, a small case e, because I want to denote the RMS value by the capital letter. And if I take the RMS value of this term, it turns out to be EP is root 2 times pi. I substitute the value of 2 pi f into this, and it is 2 pi f n1 phi max. It's easy to show this. I still substitute the value of 2 pi f into this, and then I calculate the RMS value of this term, which comes out to be EP is root 2 times pi nf n1 phi max. So the RMS value of the induced EMF can be written as I shouldn't I should avoid erasing. I want to save these notes. So the primary value on further simplification, this EP turns out to be 4.44 FN1 5 max. So this is the induced EMF in the primary. In general, this equation holds for both the primary and the secondary. So we can write this as EX, and we can write this as 4.44 F5 5 max for short, and we can write this N as T as well. We can call this as T. So this is the voltage induced in the transformer in a transformer winding. The subscript X can be either P or S, referring to primary or secondary, right? And Tx is the number of turns, Tp is the number of turns in the primary, and S is the number of turns in the secondary, and other terms have their usual meanings. So with this equation, we will proceed ahead. We know that in case of a single phase transformer, we'll derive the output equation of a single phase transformer. So if the output power is in kVA, it is Vp into Ip into 10 to the power minus 3, or it is also equal to Vs into Is into 10 to the power minus 3, right? Which is also equivalent to writing Ep into Ip into 10 to the power minus 3, or you can write this as Es into Is into 10 to the power minus 3, right? So we will use these equations. The equation for Q and the equation for Ex, to derive the equations for a single phase transformer. So if you see a typical single phase transformer, this value is known as HW, which is the height of the window. This is the window width. I have told you that this inner rectangle is known as the window, and this is the core, and the area of cross section of the iron is denoted by AI, and the window area is equal to AW. So if you see the winding arrangement for this transformer, you come to know that you have if this is the if this is the LV winding, this is the HV winding. We call the LV winding, we say that the LV winding has an area A1, and the HV winding we say it has an area of cross section A2, right? So we basically want to have the output equation for the transformer in relation to the main dimensions, right? So that is what we are interested in. So what do we do for that? We know that in single phase transformers, we know that there is a primary winding and there is a secondary winding, right? So you have half of the primary winding. If you look here, let me label this again. This is LV, this is this is LV, this is HV, and you have the LV here as well, and you have the HV here as well. So what happens? The half of the LV winding is located. You have the half of the LV winding located on one limb, and the other half is located on the other limb. See, this is the one half of the LV winding, and this is the other half, right? Similarly, you have half of the HV winding on one limb and half of the LV winding on the other limb, right? So what happens if you have to calculate the copper area in the window? The copper area in the window, that is calculated as total copper area of the primary and the secondary, right? How much area there is in the window, we say that it's total copper area primary plus secondary, right? So how do you compute this? This is equal to the number of turns of the primary winding TP times the area of cross section of the conductor in a primary conductor, right? Similarly, you have for the secondary part, you have TS, that is number of turns of the secondary, times the area of cross section of the secondary conductor. So AC comes out to be TPAP plus TSAS, right? Then we introduce this factor current density, delta, which is current per unit area And if we assume that there is the same current density in the primary and secondary windings, then delta can be written as current in the primary by area in primary, which is also equal to current in the secondary times area in the secondary. Rearranging this, you can get this AP in terms of current and the current density, and you can get AS in terms of current IP and current density delta. IS and delta. So if you substitute this equation here, what do you get? It's easy to show this. AC equals to TP times IP by delta plus TS times IS by delta, and if you take delta out, you can say that it is TP times IP plus TS times IS. And if the number of turns in the primary times the number of turns the current in the primary, if you assume that this TP times IP is equal to TS times IS, because in general these are, if the current in the primary is large, current in the secondary will be small by the same ratio. So TP IP is can be assumed to be equal to TS IS, and that can be assumed to be equal to A into T, which is the MMF, right, ampere turns. So this AC can be written as AT 280 over delta. So this AC can be written as 280 over delta, and we introduce another factor which is known as the window space factor, Kw, which is equal to copper area in the window divided by the total window area, right? So this Kw is equal to AC over AW. Then moving ahead, we can write that AC equal to Kw into AW, and the value of AC can be got from this above equation. So we can say that 280 over delta is equal to Kw AW, and then you can say that the MMF is equal to delta times Kw AW by 2. This equation we'll use in the equations that follow, so please make a note of it. And if you recall the equation for the output of the transformer Q, which we derived earlier, so we said that Q is equal to EP times IP into 10 to the power minus 3. So we introduce this term now. We say that this EP can be written as ET times TP times IP into 10 to the power minus 3, where this term ET is equal to volt per turn, right? So we can say that ET is equal to EP by TP, right? So what I have done, I have replaced EP in this equation by replaced it with ET times TP. So what does this give us? If you see that this TP IP here, isn't this the MMF? So you can say that this Q then translates to ET times AT into 10 to the power minus 3, and if you substitute the value of the MMF obtained here, you can get ET times delta times kW AW by 2 into 10 to the power minus 3, and if you substitute the value of this EP, and if you go up to the previous equation, which is this if you see EX over TX, what is this? This is 4.44 F phi m. So this is EX, sorry, ET, which we'll use later. So isn't this EX by TX equal to the ET that we have derived, right? It is the same, it is EP by TP. So we will use these values. So we say that ET is equal to 4.44 F phi m. So we will say that it is equal to 4.44 F phi m. Then we write delta kW AW by 2 into 10 to the power minus 3. So this leaves us with this equation, 2.22 F phi m delta kW AW into 10 to the power minus 3, which is the Q, or the output of the transformer in kVA. And one last manipulation that we will make to this equation, and that manipulation is that we will replace this phi with B. So what we'll do, we'll say that the maximum flux in the transformer is equal to the maximum flux density times the area of the iron, which we derived from the figure. So lastly, in conclusion, the output of the transformer comes out to be 2.22 F BM delta kW AW AI into 10 to the power minus 3. So this is the output equation. This is the output equation of a single phase core type transformer. And what does it do? It relates the output Q in kVA to which quantities? To the flux density delta flux density B, the current density, and areas AW, AI, and this KW. So it relates the output of the transformer to these parameters. Okay. Fine. So this is the output equation for a single phase core type transformer, right? It is 2.22 FBM delta KWAWAI times 10 to the power minus 3, and this is in kVA. Okay. So next we have the shell type transformer output equation for single phase shell type transformer. So the figure of this transformer is something like this. This is HW, this is WW, the width of the window. This is the just a second, I should have made this slightly neater. And this is iron area AI, and rest of the dimensions are the same as discussed in the previous slide. So in this case, what we see is that the windings are on the central limb. Both the windings are on the central limb. So if this is the shell type transformer, what do we see? You have the LV here and the HV here. This is the HV here, right? So the entire LV winding and the entire HV winding are wound on the central limb. So if you go back to see the case where we derived this copper area AC in the core type case, we used total number of turns of the conductor times the area of cross section of the conductor. So same principle we are going to use here, and we can say that copper area AC is equal to number of turns in the primary times the area of the primary conductor plus number of turns in the secondary times area of the secondary of the conductor. Knowing that these two ratios are the same and they are equal to the MMF and using the current density as well, so we come to this conclusion that this is AC is KWAW. So it is easy to show that Q in kVA for the shell type transformer is also equal to 2.22 FBM delta KWAW AI times 10 to the power minus 3. So the same equation holds for the output equation for a single phase core type transformer. Okay, so this is the output equation for the single phase core type transformer, shell type transformer. I must correct myself, this is shell type. So with this we have discussed both the cases of for output equations for single phase core and shell type transformers, right? So in the next lecture we will talk about output equations for three phase transformers, and from that we will take this discussion further. Thank you.